Okay, let's get started. This is the soil physics webinar series. This is the first of the series that we're going to have. I'm Keith Bellingham from Stevens Water Monitoring Systems, and today we are going to be talking about field installation of soil sensors in meteorological stations. We'll talk about how to protect soil sensors from surges such as lightning, and some other best management practices for going into the field for installation of soil sensors. And then the last part of this, we're going to be talking about soil water potential and soil water dynamics and some key concepts about the way water moves through soil. So let's get started. Before you go into the field, you always want to make sure that your STI-12 sensor has a unique address on it. So it's very important that each sensor has its own unique address if you have multiple sensors on an STI-12 bus. Also, before you go into the field, you want to test the probe. If you're using a logger or Campbell Scientific logger, you can go into transparent mode and just do an M command and take a reading. And typically you want to put the probe down in water and take a reading before you go into the field and see if the real dielectric permittivity is about 78 in water. And it should be clean water. You might want to get some distilled water or something. The EC parameter should be 0 or very close to 0 in pure water. Also, you want to label the cables. So if you make a probe a certain address, you want to label that so that when you go into the field that it's clear which sensor is which address. And also you want to record the serial numbers on the sensors before you go into the field. We at Stevens, we keep accurate quality control data on every single HydraProbe, and if you have the serial number, then we can better assist and better address any warranty information. So you want to record the serial numbers. And so here's a basic checklist of things that you typically want to take into the field with you. Of course, you want to get a notepad and a pen. Of course, don't forget the shovel. You're going to have to prepare a pit to get the probes into the ground. A knife, a trowel. A trowel is very good for smoothing the edge of the wall of the pit so that you can get a good installation of the soil sensor. A tape measure. You want to know the depth at which the sensor is going, so that'll be good. Zip ties, screwdrivers, tools, gloves. You also want to be mindful of how long you're going to be in the field, so you may want to take some food and water. Sometimes a Munsell color book is helpful. This color book is used by soil surveyors that sometimes the transition in the soil column as you go down, the soil properties can change, and sometimes that's indicative by the color of the soil. So that could be helpful as well to record the Munsell color of the soil where you're installing the probes. Wrench and some other tools. You want to, probably when you're installing the probes, you're also going to be putting together an enclosure and attaching a closer to a fixture. Toe tags. That's another thing you can get. You can tie them to the sensor so you can easily identify the sensors either before they go into the ground or while they're in the pit. Definitely take some wire cutters and some wire strippers. Needle nose pliers is helpful. The Explorer, which is also a helpful tool, this is available from Stevens Water. This is an STI-12 USB adapter that allow you to test the probes in the field by just connecting it to the USB on a laptop. A water bottle, it's muddy, it's going to be messy. You want to be able to wash your hands or wash off any tools with a rag and towel and a squirt bottle. Also, you will want to take a handheld voltmeter. Most SDI-12 buses are right around 12 volts, so you want to make sure that you have a way to troubleshoot the power of the system. And marker flags. After you prepare the pit, you can put some flags in the ground to know where you buried the sensors. And also some few words about site selection. Certainly you don't want to put the soil probes in a place where it could be plowed or ran over. One good resource from the U.S. Department of Agriculture is Web Soil Survey. So you can log on to this website here and you can actually get a soil map, and you can look at the properties from the soil map and make some decisions about where you're going to best put the soil profile. And it's also to be be mindful of slopes and wetlands and other considerations when you're making a decision about where to locate your soil column. In general, in agriculture, we call it an ET regime. So it's basically, what that means is a place where where you're taking a soil measurement where it's representative. For example, if you have two different crops, those are two different ET regimes. And so a soil sensor profile in one crop is not going to represent what it would be in the other crop in the adjacent field. So you would want two sites, two stations in that case. And so you just so here's just some basic guidelines for where to put it, where to put your soil monitoring station. And a couple other precautions before you go into the field. You don't want to fall in the hole, so you want to watch out for cables. There's a lot of trip hazards. Don't leave shovels and rakes laying on the ground, because you could step on them and it could fly up and hit you. This has happened to me a couple times. You want to protect yourself from the sun, the rain, and the elements, and wild animal considerations. That would include insects like bees and mosquitoes and other wild animals, bears. A lot of these a lot of these soil monitoring stations can be in remote places. And also another thing to be mindful of is augers. If you bring an auger into the field, they're heavy, that can be dangerous. So you want to be careful with any motorized auger. And so when you're installing the sensors into the soil, one of the most important things is you really want to get good contact with the soil. And in this picture here is you have the tines, the probe stuck all the way in to the soil. The soil pit the wall of the pit has been flattened with the trowel, and you push it all the way in. And then you're going to backfill the hole. And so any air gaps you have between the tine assembly, that's going to result in some error. The air gap is going to be averaged into your soil moisture measurement, and it's going to give you an error. So when you dig the pit, you could put the soil that comes out of the pit onto a tarp or maybe a cardboard box, because when you fill the pit in, you want to basically put the soil back in the hole the way it came out as best you can. I know that's always easier said than done, but and then as I said, you want to keep the ground plane flush with the wall of the soil. The ground plane is the stainless steel plate that the tines come out of, and that needs to be flush with the soil. Another helpful thing with your voltmeter, you could check the voltage on the SDI-12 bus where the sensors are wired into. You could also check the voltage on the power regulator to make sure everything is powered properly. You don't have any loose wires. Then you want to, of course, before you backfill the hole, it's very important to go over to your logger and go into transparent mode, or maybe some loggers have instructions, have an instruction built in to where you can take a reading. So go ahead and take a reading with all your sensors to make sure that the data makes sense, because once when you fill the hole, it's very difficult to take a probe out and change it out if there's a problem. So you want to take a reading and look at the data before you backfill the hole in. And with the HydraProbe, you keep it on the defaults. The only thing you should really change on the HydraProbe is the address. And the M command in STI 12 is all of the relevant parameters can be done with the M command. So then you want to refill the hole, put the dirt back in. About every 10 centimeters, you want to pack it down. You can do it with your feet or do it with a piece of wood. A 2x4 works pretty good for this. And also you want to be careful not to knock the probe out of place, or if you take a big shovel load full of dirt and plop it in there, and it could hit the cable and pull the probe out of the soil. So you just want to be careful, packing the soil back in. And then you could dip the cable. As you're filling it, you could dip the cable. And what that means is taking the cable and looping it down so that water doesn't wick down the cable and then end up, making it to the head of the sensor. You can also put the cables in conduit and then seal it off with some bentonite. This picture here is just a basic electrical conduit that's available from most hardware stores. And then your zip ties, you want to coil the unused cable. You don't want a big mess. And also you want to mount the box with the enclosure. A lot of enclosures come with mounts, or you can construct them. And then if you have excess cable, you want to coil it around the bottom post. Again, you want to avoid trip hazards. And also, one thing I'd like to add, though, is in relation to the logger and where the soil pit is, you want to make sure that there's enough cable. So if you only have 25 feet of cable on your sensor, you don't want to dig the hole for the soil pit 30 feet away, because then you'll run out of cable. So you want to be mindful of the proximity of the logger station to where the soil sensors are going to go in the ground. Now we'll talk about lightning. And lightning is one of the leading causes of failures of electronics in the field. And soil moisture sensors are particularly vulnerable to lightning. And so if you have soil sensors, we have a new method or some new recommendations for protecting soil sensors from surges and lightning. So these next couple slides are new recommendations for protecting for lightning. And a couple quick facts here about lightning. The average bolt of lightning is 3 kilometers in length and can last about 30 microseconds. It's 10 to the 13 watts, 10 to the 13th power watts. The average temperature of a lightning bolt is 25,000 degrees, and this last point is probably the most important for us, and that's the transient voltage surge, or it's also called the earth current transient, can travel up to 75 kilometers in the soil. So when a lightning strike occurs, you're seeing what it is above ground and the electrical connection between the ground and the cloud, and that transfer of electrons between the ground and the cloud. But also it travels through the soil, and it can travel through the soil up to 75 kilometers. So you have a voltage propagation that's pretty high going through the soil. And so lightning is regional. This map here shows in the United States where lightning occurs the most. You see down here in Florida, lots of lightning strikes can occur. So probably in this southwest or southeast region of the United States, you want to have more lightning protection than what you would if you were up on the Olympic Peninsula up here, where lightning almost never strikes. And then so we also mentioned, the earth ground transient, or the lightning voltage surge that travels through the ground. Different geological media has different conductivities. Of course, seawater has a very low resistance, very high conductivity. Clay is a higher conductivity or lower resistance. Loams can vary depending on its clay content and salinity. And shale and sand is less conductive, and non-saline rock is a poor conductor. But clay is generally more conductive than sand because clay can hold charge-containing ions, where in most soil morphologies, clay can develop at deeper depths as well. The soil near the surface is more organic and whatnot. So in a lot of soil profiles, the clay content can increase with depth, and also the water content can also increase with depth, and so typically what we see, soil sensors that receive damage are usually the deeper ones, and then this is the reason why. There's the higher clay content. Could be where salinity is propagated downward, or moisture. Clay can hold on to water much more strongly than sand or silts. And so, we can protect the logger station above ground, but it's also important to protect it below ground. And the point of this slide here is the earth ground transient, or the surge that propagates through the ground, is really what damages the probe. The voltage will be, the voltage surge will be propagating through the ground. It'll see the tine assembly, or the metal part of the soil sensor, and it'll get in there and wreck the circuit board. And surges will take the path of least resistance. So we offer a strategy for grounding the area around the soil sensor, so that the surge will take the path of least resistance and get shunted to ground, and not get into the probe and damage it. And so the HydraProbe is surge protected up to 4,000 volts, which it can survive. But of course, some of these surges are much higher than that we see. So above ground, you can, this is called a dual dissipator, and this can be clamped to the top of your meteorological station. You can get a copper cable and a grounding cable and attach it, clamp it to this, and then have this running to your grounding rod. You can use automotive hose clamps such as these, and it's also a good practice to double them up, so you can actually use two clamps to secure the connection, and also have a better electrical connection. And so below ground, so this is a kind of a diagram looking down at the soil pit, and here you have HydraProbes in the hole, and then here's your cable running back to your logger station. And so here in a highly lightning prone area, we'd recommend 5 grounding rods about 2 to 4 meters out from your soil pit. If you go closer than 2 meters, then you could potentially influence the soil moisture and influence the hydrology of the soil. So you don't want to get them too close, but you don't want them too far away either. So I think a happy medium there is 2 to 4 meters away from your pit. you'll want a series of grounding rods. This diagram shows 5. I know that's not always possible to get 5 in the ground, but the more you have in the ground, the more you're protected from surges through the ground. These rods can be purchased at a hardware store. These are just common grounding rods, 2 meters in length, and you can pound them 2 meters deep, and then connect them all with a copper cable, and then use the automotive hose clamps. Actually, two or three automotive hose clamps to connect these cables, and you can bury this. The cables connecting these ground rods can be underground, a couple centimeters, so no one trips over them. And then then it can all be connected to a single grounding cable, and then this can be run back to your logger station. Here's another kind of a 3-dimensional diagram of what we're talking about, protecting the soil profile with your grounding rods going 2 meters deep, and then the cable connecting all the rods going back to the logger station. So if there's a transient surge propagating through the ground, the strategy here is that it gets intercepted by one of these rods and either goes around the soil profile, or if the rods are deep enough, 2 meters, it gets down into a clay layer, or gets down deep enough to where it's all gets shunted to ground, and basically the surge goes around the electronics in the ground. So this is a diagram of how you should surge protect the logger station. Here we have our dissipators up top. Again, a copper grounding cable clamped with automotive hose clamps coming down. Here's your copper grounding cable coming from your soil moisture profile. It's connected in with this cable, which is again another grounding rod going 2 meters deep at your logger station. Most data loggers have a grounding lug, so you could take the lug and put a ground wire on it, and then bring that out of the enclosure and connect it in with the grounding system of the whole station. Another practice is to a lot of enclosures have a metal back plate that you can drill holes in to where you can mount loggers and radios and other components of your weather station. You can ground that as well, and then tie that in to the main grounding of the station. It kind of already goes over this, dissipators, your grounding rod being 2 meters deep. Here's a picture of a common grounding rod being pounded into the soil. Another thing that you can do, another tool, is this is a earth ground tester. So how these work, you can get these kits. These are roughly $2,000. So if you have a lot of stations to install, it might be a good investment, particularly if you're in the southeast of the United States and have to install a lot of stations. This might be a good investment. And how these work, there's a couple on the market. This is the Fluke 1625. You put a bunch of electrodes in the ground. There's quite a bit of cable here. There's like 50 feet of cable, and they're like little stakes. You stake them all in the ground all around, and then this little box here, it sends out a surge, and then you can connect this to the grounding system that you have, and then see how well it dissipates the surge coming from this box. You might want to, because you're putting a surge in the ground, you might want to do this before you install the soil sensors, just in case. You can read the owner's manual on this product if you decide to use it. But and so some other things about the field. If you have a probe that's non-responsive, you can check the wiring. Of course, you want to double check the address. With your voltmeter, you can check the power of the bus. I mean, most SDI 12 buses are 12 volts, and that's supplied from the logger. You could also take the voltmeter and put it in amp mode, and you could put the voltmeter leads in series with the ground wire of the bus, and see how many milliamps is being drawn from the sensors. And typically, an SDI 12 sensor will draw 1 milliamp idle, or and so if you have, for example, 12 soil sensors on there, it should be drawing 12 milliamps if it's idle. And during a duty cycle, it'll draw more. It'll draw about 10. HydraProbe will draw about 10 milliamps during a duty cycle. So you could test that and make sure there's no excessive current being drawn, nothing shorted. And again, you can communicate with the sensor itself in the SDI 12 transparent mode that's in most data loggers. And a couple other things about soil. You can have a phenomenon called perched water, where you can have what's called an aquitard or a hard pan, a soil that has a very thick bulk density, and the water can kind of perch up on top of that. And then if you have soil sensors in perched water, they're gonna stay a lot wetter than what they would be than soil sensors in a similar proximity. Sometimes you can see the wetting front move down. Ped wetting. So a ped is a unit structure of soil, and there's different kinds of peds, and they develop in soil. But usually in soil, the water will oftentimes flow around the ped before it seeps into the middle of the ped. And so sometimes you can get a soil moisture sensor kind of in between two peds, and the soil in the tine assembly may not wet up evenly. So that could explain some variation in your data. And soil is highly variable, not only with the properties, but with how the peds are arranged. Here's a photograph of peds. This is actually what's called a vertisol, which is a shrink swell clay. And the peds are the cracks between the peds get huge depending on the moisture content. And that's kind of an extreme example, but most soils, most loams have peds. And capillary forces too. So you'll have your water table, and I've seen some studies. Usually, capillary forces can draw water up from the water table a couple of centimeters. I've seen it up to an entire meter in some areas of southern Oregon. There was a study done a few years ago where capillary forces were drawing water up almost an entire meter from the water table. So, you could have a piezometer well there. You may know where the water table is, but yet capillary forces can drive water up to your soil sensors. So a couple other considerations here. This is called bioturbation, which is where a tree root or a burrowing animal can affect the probe. There's a lot of things a lot of activity in soil, biological activity in soil that can dislodge a probe. Salinity can be a factor. Bulk density is also a consideration of the soil. Some soils are very dense and don't conduct water very well, while others, such as a sand, are highly conductive. Our general recommendation is, if you see big spikes in the data, or if it gets really wet in one time step and then really dry in the other time step, it could be that a root is growing through the sensor, or an animal has dug it out. In this case, you want to, simply digging up the probe and relocating it solves a lot of problems. And then, of course, you want to backfilling the hole. And in general, soil that's disturbed has different hydrological properties. That's why we always recommend that the tie assembly get pushed into the undisturbed soil. But the head and the cable assembly does reside in soil that had been disturbed. You have to dig the pit and then put the soil back in. And oftentimes it takes, a few wetting cycles for the soil to settle back. And in this diagram here, you have a square closed packed configuration and a hexagonal closed packed configuration, and you can see the amount of spaces between these spheres are significantly different depending on how they're packed in. And over time, this is a simplified diagram of what's happening, but over time soil will settle after you fill the hole in, and as it settles, the disturbed versus undisturbed soil, a lot of things can change hydrologically, such as the porosity, tortuosity, which all affect the capillary forces in the soil. The PED structure is changed, as well as the hydraulic conductivity and where the soil saturates. All those things are affected in the undisturbed versus disturbed soil. So just be careful when you're backfilling the hole and getting it all packed in. And so the next part of this talk is I just want to say a few words about the vadozone and how water moves through soil. So the top part of the soil, it's called the vadozone, and it's the area above the water table to the surface, and it's kind of where all the action happens. And it's modeled, the way it's modeled, it's one-dimensional, so the water either goes up or it goes down. Now there is some lateral movement, but in general, the water does, it moves one-dimensionally. It moves up from evaporation and transpiration from plants, and together that's called ET, or evapotranspiration. And that's how essentially how the driving force that moves the water upward and out of the soil. And downward, gravity is pulling it down. And next couple of slides we'll go into this in a little bit more detail. And here you have your capillary rise, which is the section of the vadozone that is saturated, and that water is above the gravitational hydrostatic head, but it's water that's saturated from capillary forces, which we'll talk more about here in the next couple slides. So I wanted to talk about the significance of soil water potential. And soil water potential is an energy state, and it's the difference between the energy state of pure water and water in the soil. And pure water is said to have an energy state of 0. And the total water potential, which is represented by this Greek letter psi, is the sum of these other potentials. This is the osmotic potential, or solute potential, the pressure potential, but psi m, this is the matrix potential, is one of the most important things, and it's one of the things that can explain why water behaves the way it does in soil. And matrix potential, it's measured in terms of a pressure, so it's the amount of pressure it takes to pull water out of soil. And so the unit is pascals or hectopascals or kilopascals in some cases. It's also expressed in bar or pounds per square inch. And it's a negative number. so it's a negative pressure, and it's the product of the density of the water, the gravity, and the H is your head. And we also we oftentimes put it in units of PF, and PF is the log of the pressure. It's the log of the matrix potential in hectopascals. Sometimes when the drier the soil, the more pressure it would take to pull the water out. And in some cases, very dry soil, it's in the millions. And so having a parameter like PF makes the measurement a little bit more meaningful, makes the numbers a little more manageable, similar to like pH, for example, which is the negative log of the activity in water. This is the PF, which is the log of the matrix potential. And so, why do we have matrix potential, and what's the driving force here? And this can be explained through the chemistry of water itself. And so, water is said to be a polar molecule, and that means that there's electrons and a negative charge on the oxygen. The oxygen has two pairs of electrons around it, while the hydrogens are mostly positively charged. So a water molecule is very polar. And that means that the charge distribution, the electrical charge distribution of this molecule is very lopsided. One side's very negative and the other side's very positive. And it's said to be polar. It's a polar molecule. It's very polar. Air is nonpolar. So oxygen is nonpolar. It has an even distribution of electrons. Here's a molecule of carbon dioxide. It's very even. The same number of electrons on this side or on this side. It's very nonpolar. And so, opposites in chemistry, opposites like this don't attract. They don't want to be around each other. So this water and air don't really mix very well at the interface. And so when you have a capillary, such as a very small vessel like this is like a graduated cylinder, you have a meniscus that forms. And what's happening here is that the water near the surface, which is polar, is seeing this non-polar air, carbon dioxide, oxygen, nitrogen. It's seeing that non-polar, and it's trying to get away from it. It's being repelled from it electrically, and it's a surface tension develops with the molecules of the water at the surface, and this surface tension is strong enough to create a meniscus. So the water starts to climb the walls of the container. It would be like like a carpet in a room, and the carpet's too big for the room, and the carpet starts climbing the walls to spread out, to relax. And that's what's happening with the water in this vessel. And that's capillary forces that's driving that. The capillary forces are pushing and pulling the water to form this meniscus. And so I made this little table here sort of comparing capillary force with gravitational force. And we're all familiar with gravitational forces, but we're a little bit less familiar with capillary forces. So I made this table to kind of make some analogies to compare the differences and talk about it. So if you think of a river, gravity holds the water in the river. It's a force, and if we didn't have gravity, the water would float out of the bank and float away. But we have gravity holding the river in the bank. Well, capillary forces, this is the force that's holding the water in the soil. So it's suspended. Capillary forces is what's suspending the water in the soil. So if you have, for example, if you have a dry sponge and you put one drop of water in the dry sponge, gravity isn't going to pull it out the bottom. It's going to spread out and suspend itself in the sponge, and that's capillary forces that's causing it to spread out, and it's what's going to hold it in there. Gravitational forces pull water downhill towards the sea. And likewise with capillary forces, a capillary force will pull water down gradient from wet to dry. So there's a flow relationship with capillary forces as well. And also lastly, as water is being pulled downhill by gravity, it can hit things like dams and rocks and create rapids as it's flowing. Well, the same thing can happen in the soil. You can have, as the capillary forces are moving the water down gradient in the soil, which isn't necessarily down, like, but where it's down gradient from wet to dry, it can be slowed by the soil itself, by sorptivity. Certainly clay films can hang on to water to much greater extent than a sand would. So it too can hit obstacles and bunch up and have resistance to the capillary forces that's pulling it. And so here's a couple diagrams. Here we have a soil particle. Here's our meniscus. Soil is sometimes thought of as being a bunch of tiny little capillaries, and in some ways that's a good way of looking at it. And the soil, again, the water in the soil, again, there's a meniscus there. There's surface tension. There's capillary forces, and the soil is trying to relax. It's trying to get away from the air, so it's constantly cramming itself into smaller and smaller pores to repel the air, and that's essentially what's moving it and what's holding it in there. Now, when the water goes into the gas phase, then it evaporates and moves upward from ET. And so, at some point, as the soil gets wetter and wetter, you reach a condition called field capacity. And field capacity is this hydrological threshold in soil where the capillary forces are equal to the gravitational force. And so at some point, as the water gets wetter and wetter, you reach that field capacity. And once when it reaches that field capacity, the water will start draining downwards. Gravity will take hold and it'll start draining down, which is different than saturation. So, field capacity is usually a little less than saturation. It doesn't have to be completely saturated to be at field capacity. But it's a good threshold, and it's important. In the next couple slides, we have some diagrams of this. And so this is less than field capacity. You have the soil, the water's trying to get into the pore throats of the soil. It gets wetter and wetter. The meniscus gets bigger and bigger, and pretty soon gravity will start pulling it downward. And so here's a little graph here. So this is our soil textural triangle. So down here we have our percent sand, our percent silt is on this part of the triangle, and clay is on this side here. And you can go ahead and get your percent sand, silt, and clay to see what soil texture you are, where you fall, and basically this is a sort of a rough guide to know where your field capacity and your permanent wilting point is for your soil. So as we see here in this graph, as you get more clay rich, your field capacity goes up, as well as your permanent wilting point. So permanent wilting point is the point at which a plant can no longer take water out of soil, and that's roughly occurs about 300 hectopascals in pressure and matrix potential. So this whole line here. So as you get more clay rich, the higher the more the soil wants to hang on to the water, the higher your matrix potential would be, and also the higher your permanent wilting point. And here's your field capacity here. So it's up here. Saturation occurs, typically up around 40%, 35 to 45% typically is where you see saturation. which makes sense. If you're in a sand, water runs right through it. Your field capacity is right around 12%. So if it gets 12%, it'll start leaking out the bottom. And if you have a really clay-rich soil, clay really wants to hang on to the water. Clay is a much smaller particle than sand or silt. So there's a lot more surface area, a lot more smaller pore throats for the water to get into to relieve that surface tension due to capillary forces. And also your silt kind of occurs in the middle there. The area between your permanent wilting point and your field capacity, that's called the available water capacity. So this is kind of the area where most crops are happiest, is what's called the available water capacity. You don't want to stress it, and be in the permanent wilting point zone, but you don't want to keep it over field capacity either. There can be a lot of negative consequences for keeping it, keeping water content of the soil over field capacity if you're in an irrigation type situation, because your soil can become anoxic. And the chemistry can change quite a bit, and that could affect your crop health. So we have, of course, two products. We have the Stevens HydraProbe soil sensor, which is range of 0% dryness to saturation. It's an STI-12 sensor, and we have our Tensiomark, which is our matrix potential sensor, which has a near upward limit of close to, not exactly 10 million hectopascals, but close. Its output too is STI-12, and the matrix potential, the Stevens Tensiomark is the is heat capacitance based, so it does perform quite well in drier soils, and can get good readings into the millions of hectopascals, far beyond the limit of a tensiometer. And in general, these two pieces of data, the soil moisture and the matrix potential, are oftentimes used together. But the matrix potential is mainly an indication of when the crop needs water, and soil moisture, the volumetric water content, is useful, and it's easier to calculate how much water to put on. So oftentimes these products are used together to gain more insight into the hydrology of the soil. So the last couple slides here, I just want to talk about some data. Here we have some data. This is just a common, what commonly happens here. This is precipitation events down here. We see some rainfall events at various locations. This is about 40 days worth of data. The blue here is 20 centimeters. The green is 10 centimeters, and the yellow is 30 centimeters. And so we see the first rain event here. The 5 centimeter probe jumps up and responds, but we have a lot of ET, and the wetting front actually doesn't move down below that. So all the water in this case is retained in the top 5 centimeters of the soil. Then we have some more rain events here. We see the probe, the soil moisture data come up and go over its field capacity, and it's not being removed by ET. And so here we see after we see the sensor at 20 centimeters start to go up and become approach saturation at that point. And then that's enough water is being conducted downward. The 30 centimeter sensor is starting to respond to the water content after these rainfall events. And then we have a drying period where they dry out, and then we have some more rainfall events here after the end of the 30-day mark. So this is a pretty common, typical soil data series with rainfall and how the water evaporates out and drains. It's a pretty common wetting cycle that you see. This next slide here is data from 4 probes. So we have south and east. These probes are about, I think, 20 centimeters apart, and are at the same depths. And this is on a floodplain where you have basically totally different soil morphologies right next to one another. So you have a sandy alluvium is the south set of sensors, and you have the east is a clay-rich soil, so it's up the floodplain a little bit. And then down here again, we have a lot of rain events taking place. And what we see in the sandy soil at the 20 centimeter mark is the it's very responsive to the rain events. The east being the sandy soil, and then pretty much the east at the 33 centimeter level is just basically staying saturated. So probably capillary forces pulling water upwards from a shallow water table that's next to a river, and the drier 20 centimeters deep, it's dry most of the time, and then it responds very quickly to the rain events. Then up gradient, up the hill where the clay-rich soil is, you have which is the south. Here we see it's responding. It's just kind of gradually going upward at the 20 centimeter level in the clay soil, and then again you see very small responses to the rain events. It is responding at the 20 centimeters. The deeper 30 centimeter sensor is gradually going up. Here we see the clay. It's not reaching the saturation, not going up the same way the sand is. So different hydrologies, different soil types. And with that, I'll take some questions. And that's it. Thank you for attending. We'll have some more webinars in the near future, so stay tuned to the Stevens website and soilsensor.com for more information. If anybody has any questions, they can just email me or call me. So thank you.